Welcome to the Explainer. So today we're going to completely demystify backend architecture. We're taking a journey straight from basic database theory all the way up to practical Express integrations. If you've ever learned front-end development and then suddenly hit that wall where you're like, wait, where does all this data actually live? Well, you're exactly in the right place. We're going to transition from just thinking about spreadsheets to building real databases, specifically diving deep into relational databases, SQL, and Postgres. Okay, here's our roadmap. We've got 1. Relational concepts, 2. Essential SQL, 3. Querying and joining, 4. Postgres setup, and 5. Express integration. This layered foundation is going to guide us logically from the abstract concept of tables all the way to a practical working backend. Section 1. Relational concepts, the foundation. Okay, let's dive right into this. To build a robust backend, you really have to understand where your data lives. And honestly, the easiest way to wrap your head around this is to think of a tool we all already know, the spreadsheet. But imagine a system of connected spreadsheets that enforce strict rules, right? They validate data types perfectly and actually let you run advanced queries across multiple sheets at the exact same time. That right there is fundamentally a relational database. Unlike chaotic, unstructured data, relational databases enforce strict rules across structured tables to keep everything perfectly consistent. So, a relational database stores data in tables made up of rows and columns. Think about a mock users table. The columns define our categories, stuff like ID, name, and email. Then, the rows, well, they contain the actual records. So if we have a row with an ID of 1, the name Alice, and her email address, that entire horizontal line represents one single, distinct record in our database. But what actually makes one row different from another? That's where keys come into play. A primary key uniquely identifies every single row in a table. Think about it. Even if 2 users are named Alice, their IDs are going to be completely unique. Then on the flip side, we have foreign keys. A foreign key is just a column in one table that references a primary key in another table. For example, if you have a posts table, a user ID column would be the foreign key linking right back to the users table. So instead of copy-pasting the user's name and email onto every single post they write, which would be a mess, we just use that foreign key link. It massively reduces data duplication. This is a super vital concept in the database world, known as normalization. Section 2, Essential SQL and Data Types, Building the Walls. Now, SQL is the strict language we use to communicate with these structured tables. And let me tell you, databases care heavily about data types. Postgres, which is what we're focusing on today, is strongly typed. That means every single column must define exactly what kind of data it's allowed to accept. You've got integer for whole numbers, varchar for strings with a specific character limit, text for unlimited strings, and Boolean for your standard true or false. But check out serial. This is an incredibly useful auto-incrementing integer type that is absolutely perfect for our primary keys. Oh, and JSON, B, it's fantastic for storing flexible JSON data that you can actually query against. Choosing the correct type early on is absolutely critical. Trying to change them later? Total headache. Before we can store any data at all, we have to define the structure, and we do that using the create table command. For instance, we can define an ID as a serial primary key and a name as a varchar up to 100 characters that is not null. These extra rules, these constraints like not null or unique, they are enforced by the database itself, and this is huge. It guarantees that invalid data is physically prevented from entering your system, which honestly just proves that doing validation only in your backend code, never enough. Okay, so once the table actually exists, we can store data in it using the insert into statement. But notice what's missing when we do this. We're only inserting the name and the email. We entirely skip the ID and any created _@ timestamps. Why? Because the database handles them automatically for us. That serial constraint we talked about just magically generates the next unique ID, and a default timestamp function can grab the exact current time. It takes a ton of manual work totally off your plate. And when you want to get that data back out, you use select. This single query is incredibly powerful. Think of it kind of like a precise recipe. First, we're selecting specific columns from the users table. Next, we filter those rows down using where, and we can match specific string patterns using like. In this case, we're grabbing emails that end with @dev.io. Then we sort the results, say newest first, using order by descending. And finally, we restrict the total count to just 10 rows using limit. It's so cool. This is exactly how you surgically extract exactly what you need from a massive, massive data set. Section 3. Querying, joining, and aggregating. Visualizing the invisible. Now, I know the word join often causes beginners to totally panic. But honestly, once you visualize how they combine rows across tables using those shared keys we talked about, it makes perfect logical sense. To really demystify this, let's use a super practical analogy straight from our source material. An inner join? It's exactly like a teacher asking to see only the students who actually submitted their assignments. A left join, on the other hand, is like the teacher asking to see all the students, whether they submitted an assignment or not. Now, what's really interesting here is how it clearly contrasts pulling only users with posts against pulling all users regardless of post activity. With an inner join between users and posts, you only pull records where there is a strict match. So if a user hasn't written a single post, they just don't show up in the results at all. But with a left join, keeping the users table on the left side means all users are going to appear in your results. If they have a post, awesome, you see the post title. If they don't have a post, well, the database still returns the user record, but the post title column will just say null. Moving on to modifying data, we use update and delete. But please, guys, take this disaster warning very seriously. The where clause is your ultimate safety net. If you run an update to set a name to Bob and you accidentally forget the where clause, congratulations, every single user in your entire database is now named Bob. No joke. And the exact same goes for delete. Forgetting the where clause will catastrophically erase your entire table, literally wiped out. So always double check your where clauses. You know, databases aren't just for reading individual rows. They are absolute math powerhouses. Aggregations like count in AVG, when you combine them with group by, that's how databases powerfully process analytics and summaries. Like in this example, we are grouping all the posts by their user_ID, and then we instantly count how many posts each user has and calculate the average views of those posts. When you see a sleek dashboard online, this is exactly how those summaries are being generated behind the scenes.
Section 4. PostgreSQL Setup and Terminal. Installing the utilities.
All right, time to move from the abstract theoretical queries to actually navigating the interactive Postgres shell, which is known as PSQL. Once you have it installed and running, you can treat this as a punchy productivity cheat sheet for your terminal. You just open the terminal by typing PSQL, and from there, \L lists all your databases, \C connects to a specific one, \DT lists your tables, and \D describes the table's exact column structure and all those constraints we talked about. Pretty much every backend developer relies on these exact quick commands every single day. Section 5. Express Backend Integration. Putting on the roof. So how does an Express Node.js application actually talk to the Postgres database we just built? Usually, we use a client library like PG, but here is the real secret sauce. Instead of heavily opening a brand new database connection every single time a user makes a request, we use a connection pool. The pool essentially manages a set of already open connections and just reuses them for incoming requests. This dramatically improves performance and completely avoids massive server overhead. It's a real game changer. And this brilliantly illustrates the exact MVC architectural flow a request takes from the client URL all the way down to the database and back. This is the classic model view controller pattern. The client makes a request. Boom, it hits your route endpoint. That route triggers your controller logic. The controller then asks the model to execute our raw SQL queries. The database returns the data, and it flows all the way back up the chain to the client. As you can guess, your database design deeply affects this entire chain. Which brings us to our final thought. The absolute biggest takeaway here is that databases are not just, giant dumpsters for storing data. They enforce structure, relationships, and total data integrity. Truly understanding SQL fundamentally changes how you think as a developer. You aren't just thinking about what the user sees on a shiny screen anymore. You are thinking about the actual underlying architecture. So, I want to leave you with this question. You finally stop thinking about screens. Are you ready to start building robust, interconnected systems? Take these concepts, practice your SQL CRUD operations, and start really designing those relationships. Thanks for hanging out with me for this explainer, and keep building.